Okay, this is chapter 2, number 117, and this is kind of what the question on the test is going to be like on naming compounds and writing formulas. And so it's just a big table of information, and you have to fill in what's missing. Okay, so this is knowing your polyatomic ions. For example, like this says magnesium bicarbonate, and it asks for the cation. Well, the cation's the positive one, right? So the cation is the magnesium with a +2 charge. Okay? You know the charge because you know what group it's in on the periodic table. Bicarbonate is the anion, and so that's HCO3 with a -1 charge. And then for the formula, we'd swap and drop. And so the formula is MgHCO3 okay? And then the next one, y'all can see it gives you different information. It gives you the formula, SrCl2. What's SR? Strontium, okay? Strontium's in group 2, so it can only have a +2 charge. So when we name it, we don't have to name it strontium 2 chloride, because remember, it's not a transition metal. We can just name it strontium chloride, and so that's what I would put here, strontium chloride. And then, of course, the cation is the strontium ion, and so the way this one's doing is it's wanting the formula, but it might want like this, strontium ion, right? Or the formula, like the anion is the chloride, so it's Cl negative. Okay? Now, magnesium carbonate, is it ionic or covalent? It's a metal and a non-metal, right? Magnesium's metal, bicarbonate's non-metal. Remember, if it was a covalent compound, and looking through here, I don't think any of these are covalent, but you would name it like with the mono I'm recording here. It's not on there. That's fine. You would like carbon dioxide, etc. is how it would be named. I just realized it's not recording. But this is recording for YouTube, so that's fine. Okay? Now, I'm not going to do the whole thing because the answers are in the back of the book. Okay? That was a chapter 2 question. And then a chapter 3. So here we go. This is from chapter 3, and it's number 63. Chapter 3, number 63. And it's into chapter, right? So I'm saying this for here. You just go to the book and you go to the end of the chapter and you find the problems. In my book, it's on page 121. This one says, menthol is a flavoring agent extracted from peppermint oil. Menthol contains carbon, hydrogen, and oxygen. And then in a combustion analysis, so we take this menthol, which we don't know the formula of, carbon, hydrogen, oxygen, and y'all know in combustion we got to add oxygen so it'll burn. It produces carbon dioxide and water. And it says that we combust 10 milligrams of the substance. Milligram is going to be, takes 1,000 milligrams to equal a gram. So I'm going to, instead of working like the problem has with milligrams, y'all, I'm going to work it with grams because it doesn't give us all these 0.00000 numbers, okay? So it says we take 10 grams of the menthol and we produce 11.53 grams of water and 28.16 grams of CO2. And what we're wanting to know is the formula for this stuff. So we want to know what's the subscript of the C and the H and the O. Again, I'm using the exact same numbers from the problem, but I'm just doing it with grams. Remind me, and I know this is digging way far back, what information am I going to get from the 28.16 grams of the CO2? What is that going to tell me? How many moles of carbon, right? Remember, I'm going to get the carbon out of the CO2. What am I going to get out of the water? Yes, I'm going to get the hydrogen out of the water. So I'm going to go with the 28.16 grams of CO2. And I've got to get carbon out of there. So I know that a mole of CO2, do y'all happen to remember the molar mass of CO2 off the top of your head? It's 44.01 grams. Where'd that number come from? A carbon, which is 12.01, and an oxygen is 16, but there's two of them, right? Okay. Then I know that there's 1 mole of C in every mole of CO2. And so that gives me 0.6399 moles of C. Okay, now I'm going to work it to get the hydrogen out of the water. Same process, but different stuff, obviously. 11.53 grams of water. Do y'all remember the molar mass of water without calculating it? Or kind of calculating it real quick. How quick are y'all on molar mass?
18.
Yeah, 18-ish. Yeah, it's 18.02. And you have to be careful because water's formula is H2O. So how many hydrogens are in water?
2.
Yes, 2. There's 2 moles of hydrogen in every mole of water. Oh, shucks. So I've got 1.280 moles of H. Okay? Now, I've got the moles of the C. I've got the moles of the H. I have to get the moles of O, but the moles of O has to come from the 10 grams. Okay? So I know that 10 grams is CH and O. If I can subtract out the grams of carbon and the grams of hydrogen, it leaves me with oxygen. So I've got to take these two numbers and get grams out of them. Okay? So I know that there's 12.01 grams of carbon in every mole of carbon. That gives me 7.685 grams of carbon. And I know there's 1.01 grams of hydrogen in every mole of hydrogen. That gives me 1.293 grams of hydrogen. Okay, so I take my 10 grams that the problem gave me right here of carbon, hydrogen, and oxygen. I subtract out 7.685 grams of carbon, and I subtract out 1.293 grams of hydrogen, and that will leave me with just the oxygen. So 10 minus 7.685 minus 1.293 leaves me 1.022 grams of oxygen. I'm going to convert that to moles. A mole of oxygen is 16 grams of oxygen. And I get 0.06388 moles of O. Resume. So I have moles of everything. Once I get moles of C, moles of H, and moles of O, do y'all remember what the next step is? The ratio. Yes. You got to divide them all by the smallest number. So obviously the O is the smallest number. So I'm going to take each one of these numbers that I've underlined in red and divide it by 0.06388. Okay? That's going to give me 1 oxygen And then 1.28 divided by 0.06388 gives me 20 hydrogens. 0.6399 divided by 0.06388 gives me 10 carbons, which is my formula, C10H20O. And that, there were two different tests when we did this test for test 2. One group had this problem on their test. That might have been y'all. I don't expect y'all to remember that, but you did have a combustion analysis problem on test 2. Okay? All right, another question I had from chapter 3 is about number 65. So I'm going to work that one. Number 65, same chapter. And you guys can look it up and read it, but it says the amino acid cysteine plays an important role in the three-dimensional structure of proteins by forming disulfide bridges, which, by the way, is what makes your hair curly. It's when the protein chain breaks and the sulfurs bond and it curly hair. In a perm, that's what happened. Y'all ever got a perm? Used to be a thing now. In the early 90s, you go get a perm. I would get a perm in the 90s. I don't have to get a perm now. My hair is curly now. Anyway, TMI, right? Okay, the percent composition of cysteine is 29.74% carbon, 5.82% hydrogen, 26.41% oxygen, 11.56% nitrogen, and 26.47% sulfur. If y'all will remember, I told y'all how to work this in 3 steps. I said, assume you have 100 grams of the compound. And if you have 100 grams of the compound, then what that really means is you have 29.74 grams of carbon, right? You have 5.82 grams of hydrogen, 26.41 grams of oxygen, 11.56 grams of nitrogen, and 26.74 grams of sulfur. What do we do with grams? We convert it to moles, right? So we're going to set every one of these up to convert to moles. So I'm going to pause the video and I'm going to do this, and then when the video starts back, it's just going to all be there, okay? Okay, so I've converted each one of them to moles. And we're kind of in the same place here as we were with that combustion analysis problem. That once you get moles of each of your elements, what's your last thing you're supposed to do? You said it earlier. The ratio? You divide by the smallest. And so the smallest one is the nitrogen, 0.8251. So every one of these gets divided by 0.8251 because that's the smallest one. So the carbon, when we divide that, we'll get that there's 3 carbons. I've already done it in my calculator. So the hydrogen, we get 6.98, which is pretty close to 7. The oxygen, we get 2. And I mean, I'm getting like 2.001. So 2 oxygen, that's not a 0, that's oxygen. I'll put a little X by it. Obviously, there's 1 nitrogen and there's 1 sulfur. Okay? So there's our formula, C3H7O2NS. And a question I often get asked is, how do you know what order to write the elements? It's the problem gives them to you in this order of how I wrote them here, and so that's how I'm writing the formula. I wouldn't count it wrong if you mix that order up, but the correct way to do it would be the order they're presented in the problem, okay? Now, that number 65 also tells you that the molar mass is 121, okay? So it says the molar mass is 121. We need to add up the molar mass of this thing, C3H7O2. So we got 3 carbons, 12.01. We got 7 hydrogens, we have 32 oxygens, we have a nitrogen, and we have a sulfur. And so when I add up the molar mass of what I have, y'all, I get 121.18. And the book says it should be 121. That means I have the formula. If I had added this up and got like, what's half that? Like 60? Say I added it up and I had 60, that would tell me, well, it needs to be twice that. I would have to double all my subscripts. And that wouldn't happen here because these subscripts are 1. There's no way I could have gotten half of them. Okay? That's number 65, chapter 3. Okay? I also had a question about number 89 in that chapter. And number 89 says, consider this reaction. It gives you MnO2 plus HCl. And now it's giving you the reaction already balanced. You know, probably what I would do is say these two react, write the balanced equation, you know. It's MnCl2 plus chlorine plus 2 waters. Okay, then it says you got 0.86 moles of the MnO2, and you have 48.2 grams of the HCl. It has 2 questions. It says which reaction will be used up first, and how many grams of chlorine will you make? Okay? So when it says which reaction will be used up first, that's really asking you which one is the limiting reactant. It's just a different way to word it, okay? There's a lot of different ways to work a limiting reactant problem. And I'm just going to go, I'm going to see if y'all can tell me what to do. If not, I'll show you. And by y'all, I mean there's the students in the room, because if you're watching this, you can't talk to me. What needs to be done? Do y'all know? What did I always tell y'all about grams? Can you work with grams? As chemists, what do we got? What kind of units do we have to work with?
Moles.
We have to work with moles. So if you're totally stuck on a problem, y'all convert it to moles. There's some partial credit there. Or you get it to moles and then you just see how the numbers are going to work out. Okay, so what I could do is I could take the moles of the MnO2 and calculate how many grams of chlorine that would make. I could also take the grams of HCl and calculate how many grams of chlorine that would make. So essentially what I'm trying to remind y'all of is that grams of A to moles of A to moles of B to grams of B. Do you remember that flow chart from a couple of months ago? Okay, so I'm going to start with the MnO2. I'm going to say I've got 0.86 moles of MnO2. Move that a little. Okay, and the balanced equation tells me that I'll make a mole of chlorine for every mole of MnO2. And a mole of chlorine is, I need the molar mass, 70.9 grams of chlorine. So I get here 60.97 grams of chlorine. Grams A to moles of A to moles of B to grams of B is what I'm doing, okay? On this one I just worked, y'all, I started with my moles. So see this first little thing here? I didn't need to do that because I already had the moles of the MnO2. Okay? Now on the second one, the 48.2 grams of the HCl, Do you guys see that one starting here? So I have to go through the whole flow chart. And I'm still going to chlorine because that's what the question asks about. How much chlorine will you make? So a mole of HCl is 36.46 grams. That's molar mass. Honestly, we should know where those numbers are coming from at that point. We shouldn't be wondering, where is that? That's a molar mass. Okay, a mole of chlorine is made from every 4 moles of HCl. Do you guys remember you have to ratio the coefficients for that step? And then finally we convert to the grams of the chlorine. And we punch it in our calculator. And I get 23.43 grams of chlorine. So, I've calculated 2 different amounts for my product. Which one is the right number? Is the 60.9, can I make 60.97 grams of chlorine? Or am I only going to make 23.43 grams of chlorine? It's really the bread and the cheese and the sandwiches. Okay, so just to remind you, I'm going to say it all. 4 pieces of bread makes how many sandwiches? 2. 4 pieces of cheese makes how many sandwiches? 4. But if I have 4 breads and 4 cheeses, how many sandwiches can I make? I can just make 2 because I'm going to run out of the bread. That's my limiting reactant. So when it says how many grams of chlorine, the smaller amount of product is the right answer. And when it says, what are you going to run out of? The HCl is the limiting reactant. That's what I'm going to run out of. Okay, moving on from chapter 3, we're going to do chapter 4 now. This is number 81. And chapter 4, number 81 says, we take 30 milliliters of 0.150 molar calcium chloride, and it's written out calcium chloride, so I have to know that that is CaCl2. And we're going to add it to 15 milliliters of 0.100 molar silver nitrate. And this one gives you the formula, but on the test, I'm not going to give you the formula. I'm going to say silver nitrate, calcium chloride. Okay, first, we need to come up with a balanced equation. Do y'all remember how to do the products for that? Calcium chloride and silver nitrate? Yes, that's what I was about to, yeah, you got to swap them. And so it doesn't matter what order I write them in, but one of my products is AgCl, and the other one has to be the calcium nitrate. And of course, I have to swap and drop on that. And it says, what is the mass in grams of the AgCl precipitate? So that's what I'm wanting to know. This is another limiting reactant problem because you're told an amount for both reactants. Do y'all remember what this means? The capital M. What does that mean? It means molarity, yeah. What is molarity? What's underneath those units? Molarity is equal to, yeah, who said that? Isaac? Will? Who said that? Molarity is equal to moles per liter. Okay, so, did you not say that? You did? Okay, I thought I heard it. So do you guys see that if I take my molarity, which I'm given, and I multiply it by a volume in liters, that'll give me moles. And it goes back to what we were saying earlier. We always have to work with moles. We've got to get moles out of this information. So that's what I'm going to do. I'm going to take 30 milliliters, and I know that would be, moving at 3 decimals, would be 0.03 liters. 15 milliliters would be 0.015 liters. I'm going to multiply these together, and that's going to give me my moles for each one. 0.0045 moles. Yeah. 0.0015 moles. Okay, I just multiplied them together. Now, you know what I did not do before I started? I didn't balance this equation. And I'll say that on the test. I'll remind you to balance because it's not balanced right now. A 2 on the AgCl, and a 2 on the AgNO3. Now it's balanced. Okay? So we have moles. If we're using our flow chart, and I'm going to jump back to my previous slide, okay? If we're doing our flow chart, do you guys see that this is the part of the flow chart I need to do? I need to go from moles of A to moles of B to grams of B because I'm already at moles. So I'm going to take my 0.0045 moles of calcium chloride, and the balanced equation says, well, I'll make 2 moles of AgCl for every 1 mole of calcium chloride. And then I need to calculate the molar mass of AgCl, which is 143.32. Okay. So I calculate the amount of product with the calcium chloride. Then I also have to do it with the silver nitrate. Which one of those? I got 2 answers about the silver chloride. Which one's the right answer? Smaller amount of product is the right answer. So the 0.215, that leads back to what the limiting reactant is, the silver nitrate. Okay? There's more than one way to work this and figure out the limiting reactant. This is the way that we did most often, and when I watch you guys work it, this is the process most of y'all use. If you have a different process, that's fine with me. I want you to get the right answer and understand what you're doing, so I'm fine. Okay, the other questions I had, and I'm away from what the end of chapter ones were, but there was a question about chapter 5. There were 2 actually, and these don't require any math. This is just an explanation. It was just one question. The question says, on what law is the first law of thermodynamics based? Okay, so think back with me. What was the first law of thermodynamics? Do y'all remember? It said energy. Yes, it said energy is neither created nor destroyed, but is transferred. Okay, so the law of conservation of energy says energy is not created nor destroyed. That's what the law of conservation of energy says. But the first law of thermodynamics says energy is not created nor destroyed, but is transferred from one form to another. And you learn about that early on in physical science or physics. Remember the ball rolling down the hill? At the top of the hill, it has potential energy, right? When it starts to roll, the potential is converted to kinetic energy. And then when it hits the bottom of the hill and it's no longer rolling, there's no kinetic energy. It's been dissipated. It's back to potential, right? So all of that is saying the first law. This question also asks to explain the sign conventions in the equation, and it's this equation. And y'all will remember that Q stands for heat, and W stands for work. And remember system and surroundings? And anytime something goes into the system, that's positive. Anytime something leaves the system, that's negative because it's going into the surroundings. And so that's really what it's talking about when it says explain the sign conventions, is remember, system to surroundings is a different sign. And if the system absorbs 10 kilojoules of heat, then the surroundings had to release 10 kilojoules of heat. And so the overall change in energy is zero, because the first law of thermodynamics said it's not created nor destroyed, it's just transferred. Okay, and we did some of that with some calorimetry stuff. Okay, and that's the questions I had on that stuff.